So, well, thank you, Venkat, for the very generous introduction. I feel like I should just stop here. That was great. Um, cool. But okay, so let me get started. Yeah, so thanks everybody for coming, and yeah, thanks for the invitation. Yeah, so I'm going to talk today about locality and coding theory, in particular disjoint repair groups and lifted codes. And this talk is based on some joint work with Jabari Hastings, Amy Kahn, and Ray Lee, who are all at Stanford. Before I get started, can everyone see my pointer thingy? Cool. All right. Can I actually click? There we go. All right. Yeah. So what is this talk about? So maybe first I'll tell you what I'm actually going to talk about, just the facts, and then I'll tell you what the talk is really about with a capital A. So what am I going to talk about? So first, I'm going to talk about a few notions of locality in coding theory. So there are a bunch of different notions of locality in coding theory. The first part of the talk is going to be kind of survey-ish. I'm just going to go over a couple of them, tell you a few definitions, and I'm going to land on this definition of disjoint-repair-group-property, which is in the title of the talk, that kind of unifies a couple of other notions, is kind of at the heart of a bunch of different notions of locality in coding theory. So that'll be the first part of the talk. In the second part, I will move on to talking about some recent work. I'll talk about a couple of constructions and impossibility results for codes with these notions of locality. And the constructions are going to be based on something called lifted codes. So that gives us the other buzzword that's in the title. And so I'll talk about those when we get there. So those are the things that I'm actually going to talk about. What is the talk really about? Like, what do I hope that you take away from it? So here are some of the things that I hope that you, meaning the WOLA audience, so local algorithms folks, take away from this talk. So in particular, I'm not assuming a coding theory audience. I'm assuming a local algorithms audience. I hope that's appropriate. So the things that I hope that you take away from this talk are, first, if you haven't seen the disjoint-repair-group-property before, I hope you get that. And I want to give you like a flavor of the sorts of constructions and bounds and the types of questions that folks are thinking about in this space. But the real thing that I want you to take away from this talk is perhaps inspiration to maybe use these notions of locality or these sorts of codes in your own work. So as we all know, error correcting codes are super useful for a variety of applications, and in particular for algorithmic applications. And this notion of the disjoint repair group property and related notions of locality, they do have applications, but I feel like they should have more applications. So I think that's really what this talk is about with the capital A. That's the point of this talk, is that it's kind of an advertisement, or it's meant to be an advertisement for these notions of locality and maybe an invitation for folks to find even more applications of them. Okay, so that's what the talk is about. Real quick outline. So I'm going to just start by talking about some notions of locality and error correcting codes. I'll focus on a couple of different notions, including locally decodable codes and locally repairable codes. And then in part 2, which is really the second half of part 1, I guess, we'll focus in on this notion of disjoint repair groups and also a related notion called batch codes, which I think are kind of at the heart of some of these other notions of locality. And then in the second part of the talk, which here is labeled part 3, I will then talk about some recent work, including some constructions of codes that have lots of disjoint repair groups, as well as some new impossibility results. Right. And throughout, please ask questions. Yeah, so I see this is a not too large a crowd. So yeah, just please feel free to unmute yourself, ask questions. If you want to ask in the chat, go ahead. I'll try to keep an eye on it. And if I don't, I'm sure someone else will.
Yeah, I'm keeping an eye on the chat, maybe. So
thanks, Venkat. Cool. Yeah, so ask questions, either unmute yourself and just ask, or put them in the chat. Yeah, I'm hoping to keep this talk pretty high level, more of a survey-ish overview kind of thing, just to give you a flavor of what's going on. But the danger with that is that I might be omitting some details which are necessary to understand things. So if I do that, just please interrupt me, because I want everybody to understand everything. Okay, so this is what we're going to talk about. Let's get started. Okay, so yeah, part 1, codes and locality. So I've been using the phrase error correcting codes a lot so far. What do I mean by that, and what do I mean by locality in error correcting codes? So for the purposes of this talk, a code is just a map from f to the k to f to the n. So here f is just some finite set. It's actually going to be a finite field for most of the talk, for all of the talk. And k is some integer that is less than n. So the picture looks like this. I've got some message X. I'm going to refer to X here as the message or the data. Think of this as something that you want to send or something that you want to store. And you're going to encode it with the code C to obtain a code word, little c, which is big C of X. And this is a longer code word. It's of length n, which is longer than the original length k. And the basic hope with error correcting codes is that what you're doing here when you do this transformation is that you're adding redundancy. So you take your original message and you add some redundancy to it with the goal of protecting this data from errors or erasures or some other sort of corruption. So if something bad happens to some of the symbols over here, you hope that there's still enough information to allow you to recover the original message. In this talk, I'm going to focus on linear and systematic codes. So by linear, I mean that F is going to be a finite field, and this map C here is just going to be linear over that finite field. So you can think of the encoding map then as just multiplying this vector by some matrix. And when I say systematic, I mean that the input X actually appears as the first K symbols of the output here. So if X is this yellow vector, then X would appear again here, and then I'd have these sort of extra redundant symbols that I'm adding on at the end. The reason to make this systematic for this talk is mostly just for convenience. There are a bunch of different subtleties that crop up depending on whether you're talking about wanting things to be message symbols or code word symbols or whatever, and asserting that things are systematic allows me to sweep some of those under the rug. So that's basically the reason that I'm saying this, is just so I can avoid getting into some subtleties. But they might come up a little bit, but hopefully not. But okay, yeah, so for now, codes are linear, systematic. They look like this. Everyone good on what I mean when I say a code? Cool. All right, so what do I mean by locality in codes? So informally, I say that a code exhibits locality if I can recover any one symbol of the message from not too much access to the code word. So for example, say I want this symbol from the message, just xi, I don't want the entire message. I should be able to get that by maybe making just a few queries to my code word. Say I query here and here and here, and I should be able to recover xi. So as stated, this seems like kind of a silly notion because I just said this code was systematic, so xi is sitting right there. I shouldn't have to query these three things in purple boxes. I could just query that thing there. So the thing that makes this definition interesting and also useful is that I should be able to do this even in the presence of some corruption, so even in the presence of errors or erasures. So for example, let's say that symbol that I wanted actually got erased. I don't know what it is anymore. I should still be able to recover it from just a few queries to my code word. Okay, so that's sort of an informal definition of locality. For a formal definition of locality, there are rather a lot of them. So here are just a few notions of locality in coding theory. And if you Google local codes, you also get way more options of locality in coding theory. I'm not going to talk about most of these, but what I am going to talk about is two of these notions, locally decodable codes and locally repairable codes. And these are pretty different notions within the small area of locality in coding theory. And after I introduce those notions, those are kind of as motivation, I'm going to introduce the disjoint-repair-group-property, which kind of underlies both of those different notions. So it's something that they have in common. And while I'm at it, I'm also going to mention batch codes, which are related to the disjoint-repair-group-property. So that's the plan. I'll talk about just these two notions and then say something that kind of underpins them. Okay, so locally decodable codes. So these were first introduced by Katz and Trevisan in 2000, first officially introduced, but they've actually been used implicitly way before then and throughout theoretical computer science and cryptography. And the basic idea is that we should be able to recover the symbol that we're looking at, even in the presence of a constant fraction of errors. So suppose I want this symbol, xi. The model is that even if a bad guy comes along and corrupts a constant fraction of symbols here, so these x's mean that these have been changed to something else, something that they're not supposed to be, but I don't know which ones were changed. So there's some sort of silent failures, silent errors. So even if some bad guy does this, I want to be able to make some queries to this code word. In this case, the queries may be randomized, and in fact, necessarily must be randomized, or else the bad guy would just clobber the deterministic places that I would query. So I make these randomized queries to my code word, and I'm supposed to recover xi with high probability. And if I can do that for any symbol xi, I say that my code is a locally decodable code. Definition makes sense? Cool. All right, so I'm not going to talk too much about locally decodable codes other than as motivation for disjoint repair groups, which I'm going to mention in a moment. But they come up in a lot of different places in theoretical computer science and cryptography, notably in private information retrieval and hardness amplification, and sort of throughout complexity theory and pseudorandomness. So it's a pretty fundamental notion at this point. Here is a different notion of locality in coding theory with a very different flavor. And this is a more recent notion just in the past, I guess, past decade or so, motivated by distributed storage. This is the notion of a locally repairable code. Omer A asks in the chat, are the errors assumed to be in random locations? That's a great question. No, they are adversarial. So a bad guy chooses them. So there is no probability. So the model is a bad guy tells me which I have to recover, and then a bad guy decides which symbols are corrupted and how they are corrupted, and then I get to flip some coins after the bad guy's decision and try to recover. Does that make sense? Oh, what is with high probability in the definition? That's with high probability over my randomized queries. Great. Okay. Well, yeah. Thanks. Yeah, and please do. Stop me and ask questions. Like I said, I'm not throwing up like super technical definitions, but that means that it's I think it's easy to misunderstand. So, thanks so much. Yeah, please keep asking questions like that. Okay. So that's locally decodable codes. Locally repairable codes are a much weaker notion of locality in that I have to deal with a much sort of weaker adversary. We were just talking about how this adversary in the locally decodable codes setting gets to introduce a constant fraction of errors. Now the bad guy gets to introduce only a single erasure. So the model here is that I have some symbol that I want, xi, but now the bad guy is not going to corrupt anything beyond xi itself. They're just going to erase xi. So I can see everything in the code word except xi, and my goal is, as before, to make at most 2 Q queries. This time they can be deterministic, and I want to recover xi from those queries. This notion makes sense? Okay, so this is a much weaker notion than locally decodable codes. Why do we care about such a notion? So the motivation originally comes from distributed storage. So the setup here is that I've got some data that I want to store, and I want to store it in a distributed way, so on a bunch of different distributed nodes, a bunch of different storage nodes. So what am I going to do? I'm going to encode my data with an error-correcting code. So X is going to turn into this code word C, which is just X with some redundancy on it. And then I'm going to take each one of these symbols and send them out to a different one of these storage nodes. And the reason that I do this is so that even if one of these storage nodes fails, like that, let's say, that I don't lose data. The point of the error correcting code is that I'm adding this redundancy so that even in the case of one failure, I can figure out what the original message was. Or ideally, in the case of even more than one failure, I should be able to figure out what the original message was. But let's say for a moment that there is only one failure. In that case, in these systems, the thing that you would like to do is repair that failure. So maybe you want to set up a replacement storage node, which still has that information on it. So you want to recover this xi from the data that's left. And ideally, you'd like to do it while contacting as few other nodes as possible. And the reason for that, well, there are a couple of reasons. One is that you want to limit the amount of bandwidth that you have to use to communicate with. And the other reason is that the more nodes you contact, the more likely it is that one of them is going to be pretty slow. And so if you contact fewer, you'll get your answers faster. So for a variety of reasons, you want to contact as few nodes as possible. And here we are back at this definition of a locally repairable code. where there's for any one failure, I want to be able to recover that data by looking at just a few other symbols. Motivation make sense? Okay, so that's locally recoverable code or locally repairable codes. They're the same thing and they have the same acronym, so I might use them back and forth, sorry. I'll just say LRCs. So that's LRCs. So now we can talk about LRCs with availability, which is a slight strengthening of this notion. So this is the same thing as an LRC, except that instead of being able to recover my erasure, or instead of being able to recover xi in just one way with Q queries, I want to be able to recover it in multiple disjoint ways. So for example, in this picture, maybe I want to recover xi, it's been erased. Let's say I can recover it by looking at these symbols. And then I also want to be able to recover it by looking at those symbols, which do not overlap with these ones. And typically in this context, t, the number of these disjoint ways to do this repair, is going to be some constant, like 2 or 3 or something like that. Definition make sense? Cool. Okay, so why would we want this? Well, there are a couple of reasons. Oh, actually, sorry. First, I'm going to refer to each one of these things as a repair group. So what I'm asking here is that each symbol should have t-disjoint repair groups for t, some constant. So why do I care about this? There's a couple of different reasons. I can illustrate them both in the context of distributed storage. So the first one is pretty similar to the previous motivation. So I'm sitting here with my distributed storage system and some node fails and I want to be able to recover that symbol. Well, I can do it by looking at these two symbols, just like before. However, what happens if another node fails or is unavailable for some reason? Then I can't use this repair group. So if I have another disjoint repair group hanging around, that's convenient because I can use that to recover the data that I'm after. So having multiple disjoint repair groups gives you flexibility in case more than one node is unavailable. Another motivation, which doesn't involve any explosions, but is morally the same thing, is being able to serve the same query multiple times to multiple different clients without having too much load on any one server. So for example, suppose that this client here wants this data. This storage node can serve that request, but now it's busy. If someone else comes along and also wants the same data, if I have another repair group available, they can contact just those couple of nodes and get the data that they're after. Those ones become busy. And then if I have some other client who wants more data, they can, again, just contact, take another one of those disjoint repair groups and download that data. So it sort of allows you to handle multiple queries at the same time. So motivation makes sense. Definition of LRCs with availability makes sense. Okay. Cool. Okay, yeah, so quick recap. We talked about two different notions of locality in coding theory motivated by very different things and seemingly pretty different. One is much stronger than the other. So we talked about locally decodable codes where you want to find a single symbol xi given a constant fraction of errors, and locally repairable codes where you want to find xi just given a single erasure, but possibly in a few disjoint ways. Oh, there's a question in the chat. So I have a basic question. If you know xi, what does it mean to query xi? Do you mean you have some key associated to xi and you want to fetch the data related to this key? Oh, sorry, I'm probably misspeaking a bunch. I guess you're technically querying I, that you're querying location I, and the data is xi. So I guess like I is the key and xi is the data. Does that make sense? Great. Yeah, sorry about that. I'll try to be consistent, but throughout x is always going to refer to like some data, and xi is always the data, and the index I is the thing that I'm interested in. Cool. Right. Okay, so we have these two notions of locality, which seem pretty different, but it turns out that they actually kind of have the same thing, sort of combinatorially speaking, going on at the heart of them. And that's that they both have to do with having some disjoint repair groups for every symbol. So that's kind of obvious when I talked about LRCs with availability. I think I actually used the phrase disjoint repair groups, but it turns out that it comes up in locally decodable codes too. So that's what I'm going to talk about next, is I'll introduce this notion of the disjoint repair group property and show how it kind of underpins both of these various definitions of locality. Okay, so what is the disjoint repair group property? Well, it is that there are a lot of disjoint repair groups. It's pretty self-explanatory. So we say that a code C has the t-Disjoint-Repair-Group-Property, or t-DRGP, if for any I, we can recover xi, so this symbol that we want, in t-disjoint ways other than xi itself. So we're in this setting where xi got erased, just like in an LRC, and just like in an LRC with availability, I want to recover xi using t different repair groups. So maybe this repair group can give me xi, and this disjoint one can also give me xi. So the main difference here between this and a LRC with availability is here I'm thinking that t might actually be much larger than a constant, and additionally I'm not putting any explicit restriction on the size of the repair groups. Just to note, there are various different ways that this definition is given in the literature. So in some instantiations, you are allowed to query xi itself, in which case replace t with a t+1, you get the same thing. In other instantiations, you want to be able to do this for any symbol of the code word, not just any symbol of the message. I'm hoping that by making it systematic, I can kind of sweep that difference under the rug. But let's go with this one for this talk. Okay, and like I said before, this notion kind of underpins both of those two disparate notions of locality that we already had. So for small t, when t is a constant, this is pretty similar to LRCs with availability, like we said before. Basically, you just want t-disjoint repair groups. That's exactly what this property says. On the other hand, for large t, when t is omega of n, this is actually equivalent to a locally decodable code. So to see one side of this equivalence, let's return to this picture that we keep having. Suppose I want to recover xi, and I'm in the locally decodable code setting, so some adversary is going to corrupt a constant fraction of the symbols. Now, suppose that this code has omega of n disjoint repair groups for this symbol xi, so it has a lot of disjoint repair groups. So say that here are all of the different ways that I could recover xi. I claim that this is immediately going to give me a scheme to do the local decoding, and that scheme is basically just pick a random repair group. That is, since there's a omega of n of these random repair groups, sorry, there are omega of n of these repair groups. So on average, they are constant sized. So if I pick one at random, with pretty decent probability, I'm going to completely miss the constant fraction of errors that were introduced, and then I can just recover xi because I have no errors in this particular repair group. So if I have omega of n repair groups, so if t equals omega of n, then I have an LDC. Right? So as t goes from constant to omega of n, I kind of interpolate between LRC and LDC. The disjoint repair groups also show up in a bunch of other notions of locality that appear throughout the literature and coding theory. So one of them is PIR codes, which are used for coded private information retrieval. I'm not going to talk about those. Another place where they show up is batch codes, which I am going to mention briefly. So batch codes were introduced by Ishai, Kushlevas, Ostrovsky, and Sahai in 2004 with some motivations in cryptography for private information retrieval. But they smell pretty similar to this disjoint repair group notion. So actually what I'm going to describe here technically is a primitive multiset batch code, but I'm just going to drop those adjectives because I'm not going to contrast them with anything else. So the definition of a batch code is the following. Now, instead of querying just one thing, I want to be able to query t things, some multiset of t queries, I1, I2, up through it. And I want to be able to get that data in disjoint ways. So for example, let's say my first query is xi, just like before. Let's say my second query is xi again. Think of this as another user showing up and saying, hey, I also want xi. Then there's some other query xj and so on, but xj might be different. Then the guarantee that we should have is that for each one of these queries, I should be able to get it in some disjoint way from my underlying, from the code word. So for example, maybe I can get xi from xi itself, but to get my second copy of xi, well, this xi is busy, so maybe I'll get it from these code word symbols. And then to get xj, maybe I'll get them from over there or something like that. So this is a stronger notion than the disjoint repair group property. For the disjoint repair group property, this multiset would just be I, and I want to get all of those things in disjoint ways. Now I want to get these t things, which might be all the same, but might include some different ones in disjoint ways. Does this definition make sense? Cool. Yeah, so this smells very much like the disjoint repair groups thing, just a little bit stronger. And applications for this, so the same load balancing application that we had before applies here as well. Like if you have clients who want to query I1 and I2 and I3 and so on, this will allow them to do it all at the same time. There's also some applications in private information retrieval, which was one of the original motivations of this paper, and so on. Okay, so those are the notions of locality that I wanted to talk about. So far I talked about a couple of different buzzwords of locality in coding theory, and then I said that, all right, really this notion of disjoint repair groups, this is kind of at the heart of a lot of them. And I guess going back to what I said before about what this talk is about with a capital A, that's one thing that I want you to take away from this, is that it's sort of interesting to think about codes that have this particular combinatorial structure where every single symbol has multiple disjoint repair groups. What I want to talk about sort of going forward in the talk is, okay, now that we understand this definition, like what do we actually care about this definition? Like what are we trying to do? So what are the questions we want to answer? So in general, as with a lot of things in coding theory, we want to understand like what are the best trade-offs we can get, and what are the parameters that we care about. So we want to understand the best trade-offs between, first, the locality, so that's the size of the repair groups, the availability t, that's the number of the repair groups, so we'd like t to be as large as possible, and the redundancy n minus k, that's the number of extra symbols we need to store. So this yellow block is k symbols, and this whole thing is n symbols. So n minus k is like all of these extra blue symbols that we need to store. So we'd like that to be as small as possible. For example, in the distributed storage setting, every sort of extra symbol of redundancy is one extra storage node that you need to use. So there are lots of things that we might care about other than just these. For example, we might also want the distance of the code to be good and other things like that. But already just thinking about these three things is really interesting. And actually, I'm just even going to focus on two of them, just the availability t and the redundancy n minus k, because already the trade-off between these two things is really interesting and really hard. And also, generally, when you can come up with a construction that has good availability, it typically also happens to have pretty good locality for free. So it makes sense to kind of just focus on these two things. So for the rest of the talk, I'm going to focus on this trade-off between availability and redundancy. And for the rest of the talk, I'm going to draw this trade-off on some plot. So on the x-axis, I'm going to have availability, and on the y-axis, I'm going to have redundancy. And I'm going to plot these as a log plot, so log base n. So just to make sure that we understand what points on this plot mean, if I were to plop a point here on this plot, let's say at 1/2, 3/4, this point would correspond to like a hypothetical code that has redundancy n to the 3/4 and with root n disjoint repair groups. So this is kind of halfway between the Lrc setting and the LDC setting. The Lrc setting would be over here with like a constant number of repair groups, and the LDC setting is over here with omega of n repair groups. Here is root n repair groups, kind of in the middle. Having redundancy n minus k equals n to the 3/4. Well, we'll see how good that is in a moment, but it's better than omega of n, but not as good as like log n. So, does this plot make sense? I'm going to be showing this up and putting points on it as we go forward, so I want to make sure this makes sense before we move on. And just for a sanity check, we want points to go in this direction. So more availability, more repair groups, less redundancy. Okay, so with that, I think I've finished my sort of overview of notions of locality and what we care about. I'm going to start moving into some actual constructions and bounds. Are there any questions before I move on? Okay, cool. Yeah, so let's plow ahead then. So I'm going to start by talking about constructions, and let's start with sort of a pretty simple construction that does a pretty good job, and that will motivate our further constructions. And this is bivariate Reed-Muller codes. So if you haven't heard of a Reed-Muller code before, it does not matter. I will define it. So here's how this works. Let's let f be a finite field of size q. And I'm going to associate my data x with a bivariate polynomial f of xy with total degree at most or strictly less than q minus 1. So that is, I'm going to write f of xy as the sum over I and j of fij x to the I, y to the j, where the sum is over all I and j, so that I plus j is strictly less than q minus 1. So I can think about these fij's here, these coefficients, as being my data. And so I'm going to arrange those sort of like this, where here's I and here's j, and this is the coefficient fij. And I ranges from 0 to q minus 2, and j ranges from 0 to q minus 2, and we have the constraint that the sum of the two is always going to be strictly less than q minus 1. So that's why I get this little triangle-y thing here. So before I was drawing this as like a bar of length k, now I'm drawing it as this little triangle thing for reasons that'll be clear in a moment. Right. So this is going to be my message x. And so k here is the number of symbols I have in my message. In this case, that's just q minus 1 plus 2 choose 2, which is about q squared over 2. Now we can define the bivariate Reed-Muller code C, which maps this message into f to the q squared as the code which just takes this message, treats it as a polynomial, and evaluates it at all of the points. So I'm going to end up with a grid that looks like this. So the alpha beta position is indexed by f of alpha beta. And so this is the Reed-Muller code. This is a classic code in coding theory. Definition makes sense for folks who haven't seen it before? Cool. Okay, yeah, and the block length here, sorry, the length of the code, n, which is, before I was drawing it as some big blue rectangle of length n, now n is going to be q squared because I have q squared symbols in this block over here. I said at the beginning that I was going to think about systematic codes. The way I've described this, it's not systematic. These symbols don't appear over here, but you can do some linear algebra and make it systematic. This is just like an easier way to think about it. So just pretend that it simultaneously has this encoding map and it's systematic. It's morally okay. So let's just do that. Okay, so why are we looking at bivariate Reed-Muller codes? Well, I claim that they have this disjoint repair group property that we want. In particular, I claim that each symbol of the code word, and if I had a systematic version, in particular, each symbol of the message, has q minus 1, which is about root n disjoint repair groups. And to see that, let's look at this picture here. So here's a symbol that, let's say I want to recover this symbol. So I want to come up with q minus 1 disjoint repair groups for it. So the way I'm going to do it is I'm just going to look at a line through this symbol. So this is a line in fq squared. So I look at this line, so I can parameterize it as L1 of t, comma L2 of t through this point, alpha beta. And because we're in some finite field, maybe it wraps around or something, but let's say a line looks like this. And I claim that this line is going to give us a repair group for this symbol. And the reason is that if we think about the symbols that appear on this line, that's what we get when we take our original polynomial f and just compose it with the line. So we're going to get a univariate polynomial g, which looks like the sum over I and j of fij, L1 of t to the I, L2 of t to the j. And since L1 and L2 are both linear functions, it's just a line, this whole thing is a univariate polynomial of degree strictly less than q minus 1. And fun fact, if you haven't seen this before, if you have any polynomial in a finite field of size q of degrees strictly less than q minus 1, if you add it up, if you add up all the evaluations of that univariate polynomial, you're going to get 0. It's just nice symmetry thing in finite fields. So what that means is that for any line like this, all of the symbols on this line are going to add to 0 in any legitimate Reed-Muller code word. Therefore, I can recover this symbol by looking at the pink symbols by just taking the sum and taking minus that. That'll give me this symbol. So therefore, the pink symbols are going to give me a repair group for the orange symbol. Does this make sense? Cool. Okay, so now I can have, right, I claimed that I had q minus 1 disjoint repair groups, and that's just because there are q minus 1 disjoint lines that go through any particular point. So for example, here's another line. This is also a repair group for this point, and it's disjoint from the one I already had. Right, so now this bivariate Reed-Muller code, it gives me this, has this disjoint repair group property. I have about root n disjoint repair groups. That's pretty cool. The downside is that the redundancy is pretty large. So the redundancy n minus k is at least n over 2, because k here is less than or equal to q squared over 2, and n, which is the number of the blue boxes, is q squared, which is n. So the redundancy is like n over 2. So that's not great. We would like to do better than that. But at least let's record this on our plot to see how well we're doing. Right, so here's where we're going to plop our bivariate Reed-Muller code. Right, and so it has root n disjoint repair groups, so it's at this 1/2 point, and the redundancy is omega of n, so it's way up here at 1, which is not great. So we'd like to do better. And this is where the other buzzword in the title of the talk, lifted codes, come in. So we can do better using something called lifted codes. Oh, actually, wait, sorry. There's also, it turns out you can basically interpolate between the bivariate Reed-Muller code and a point down here, which is also attained by a pretty simple construction, using a nice approach using combinatorial designs from Fazeli, Vardy, and Jacobi in 2015. So there exist codes sort of all along this line that meet this trade-off. So our question here is can we do better? And in fact, we can using something called lifted codes. So what are these? These were introduced by Gulkarparty in Sudan in 2013. And here's the basic idea. So once again, let's consider a finite field of size q. And now I'm still going to associate my data x with a polynomial, f of xy, so some bivariate polynomial. But now, instead of saying that I want the degree to be strictly less than q minus 1, what I'm going to do is I'm just going to enforce exactly the property that I wanted in order for the disjoint repair group thing to work. So I want that for any line L, when I take f and I restrict it to that line, I get a low degree polynomial. So as we saw before, if you start with a low degree polynomial to begin with, and you restrict it to a line, of course you get a low degree polynomial. And the question is, if I relax my requirement from being a low degree polynomial to begin with to just having this property, like, do I get anything more? Can I get less redundancy? So the question is, are there high degree polynomials f of xy so that every restriction to a line is low degree? If you think about this for a minute, if you haven't seen this before, I think your intuition might be that there are not such high degree polynomials. In fact, that there are not over the reals, there are not over prime fields even. But it turns out that over fields of small characteristic, actually, there are such polynomials, which I found very surprising when I first learned it, and there are a lot of them. And this is a result of Gulkarparty in Sudan, is that when the characteristic of your field is pretty small, so that is, your field has size, let's say 2 to the t or something like that, t is already used, 2 to the l or something like that, then actually this restriction is weaker than this restriction. So this is a new code, which is pretty cool. So what does this look like? So before I had my message symbols that I thought of just as coefficients of some polynomial, but now it turns out actually there are lots of high degree polynomials that happen to restrict to a low degree polynomial on any given line. And that allows us to add a whole bunch more coefficients that we could possibly use. Right? So it turns out that, and this is just a cartoon, not an actual diagram, but there are a bunch more coefficients up here that you could add in and make polynomials so that they still restrict to a low degree polynomial along any line. And given that fact, we can now define a lifted code. In this case, it's a lifted parity check code in exactly the same way that we defined a read Muller code. We just take this polynomial and we evaluate it at all of the points. And that's going to give us this grid of evaluations just like before. And since the thing that we demanded was exactly the property that we needed for this disjoint repair group thing to go through, namely that when I look at any line, I'm going to get this nice repair group for any point on it, I still have this Q-1 disjoint repair group property, or this root n disjoint repair group property. Does this make sense? Cool. So I think this is really cool. It's just like you look at the read Muller code, you say, okay, what exactly do we want from it? Okay, now take the biggest code that has that property. It turns out it's actually way bigger. So now we have the same availability, but better redundancy. And if you plot that on this plot here, it's going to be down here. So we actually get an asymptotic improvement in the redundancy. Instead of the redundancy being omega of n, now the redundancy is actually little o of n. It's like n to the 0.792 ... This number turns out to be the log base 4 of 3, which, yeah, I can explain why later if you care. So the question is, why is the redundancy reduced? Can you give an intuition? Yeah, so the intuition comes from this previous slide here. Or sorry, are you asking why is it the case that the answer to this question is yes? Or are you asking why is it the case that given that the answer to this question is yes, the redundancy is reduced? Okay, the second, right? Yeah, so given that the answer to this question is yes, basically what this picture is saying is I can now have a high degree polynomial that still has this property. And let's just say that I had all of the monomials that I had before, so x to the I, y to the j, where I plus j is strictly less than q-1. But now, let's say I'm also just going to throw in there x to the q-1 over 3, or x to the 2q-1 over 3, y to the 2q-1 over 3, or something like that, or even x to the q-2, y to the q-2, something like that. I can throw in some additional high degree monomial that will still allow me to have this property. And when I throw in that additional high degree monomial, that basically gives me an additional message symbol without costing me any more code word symbols. So I'm increasing the number of yellow squares and not increasing the number of blue squares. And the redundancy is defined as number of blue squares minus number of yellow squares. So the redundancy is going to go down. Does that make sense? Awesome. Cool. Yeah, so basically this is allowing us to get more yellow squares, more message symbols, less redundancy. And it turns out it's like dramatically less redundancy. So it goes from omega of n to little o of n. Great. Oh, okay. I am running rapidly out of time. So maybe I'll just finish mentioning these constructions. Okay, so yeah, so far everything I've talked about is previous work. What is new here? So one question that you might ask is, all right, so we see that we can do better using lifted codes like this. Can we, does this generalize beyond just this point? So if you take lifted codes with more variables, so it makes sense also to look at like trivariate lifted codes or m-variate lifted codes more generally. So start with the m-variate read Muller code and lift that. Then you're going to get a bunch of points out here. That sort of naturally generalizes. There's not really a natural generalization that goes down here. And the reason is that this root n is kind of coming from the fact that the root is, the square root is 1 over 2, where 2 is the number of variables. So if you wanted to get down here or something, you would need like a fractional number of variables if you want to just blindly go ahead and try to adapt this, so that doesn't make any sense. But it turns out that you can using something called lifted multiplicity codes. And so this is joint work with myself and Ray Lee. I'm not going to talk about these, but basically the idea is you can throw in some derivative information and basically interpolate between this point here and that point down there. So we have constructions that live on this line all the way down. A downside of these codes is that they actually have really big alphabet size, which is not super practical. All of these other codes can be made binary with basically no loss in parameters, but if you try to make this construction binary, you get a line that that looks like this, which doesn't look so good. So you might ask, okay, can we interpolate and even get codes over small alphabets? So by alphabet, I mean like the size of the field that you're working over. And turns out you can. This is some other recent work, which is joint with Jabari Hastings, Amy Kahn, and Ray Lee. And this is a notion called wedge lifted codes. So it's kind of a riff on lifted codes. So once again, we're going to associate our data with a polynomial, a bivariate polynomial, f of x, y. Again, we're not going to demand that this polynomial be low degree. We're not even going to demand that it restricts to a low degree polynomial on every line. Instead, what we're going to demand is that it sort of restricts to a low degree polynomial on any collection of lines, in the sense that for any appropriate collection of lines, which we call a wedge, because visually you think of it as like a wedge of lines, when you take that polynomial and you sum it over all of the lines in the wedge, then what you get is low degree. So this has the potential to allow for maybe some higher order terms to cancel or something like that when you take two polynomials that might not be low degree on these two lines and add them together. And it turns out that actually using a construction like this, you can in fact get even more message symbols, even more yellow squares. There are even more high degree polynomials that have this property, so that when you restrict them to a wedge in this notion, you get a low degree polynomial. Yeah, so here's my illustration of a wedge. You take multiple lines and you say that when I restrict to this line plus what I get when I restrict to that line, that better be low degree. When you do that, you get even more yellow squares, even less redundancy. And this still has the disjoint repair group property, now with slightly larger repair groups, because this is basically saying it should pass a parity check on these highlighted squares. So the sum of all of these highlighted squares plus this guy should be equal to 0. And then we define the wedge lifted code as before. And so with that, we're able to get some further improved, or some nice constructions here. Yeah, here's the technical version, but the non-technical version is this picture. So it doesn't quite meet the lifted multiplicity codes line that we had before, but we can get it over a binary alphabet instead of over a huge enormous alphabet. So it's getting closer. Okay, so I'm out of time. So let me wrap up real quick by just mentioning what is optimal. What are the sorts of lower bounds available? Oh yeah, so what is the takeaway that I want you guys to get from this? So I guess the takeaway is that we actually have pretty good constructions of codes with many disjoint repair groups. And one way to get them is kind of riffing on this notion of lifted codes, which sort of hinges on this really interesting and surprising fact that there are actually tons of high degree polynomials whose restrictions to smaller objects all happen to be low degree. Yeah, so let me just wrap up real quick by saying, is this optimal? Like, have we found the right or close to the right answers? And the answer is, I don't know. For t-disjoint repair groups, essentially the best lower bound that we have is this one here on this plot. So we know that the redundancy must be at least root n, but as t grows, this bound doesn't depend on t at all. So this is pretty depressing state of affairs. For batch codes, which I mentioned earlier, so remember that's basically like t-Disjoint-Repair-Group codes, except the queries might be different things instead of all the same thing. Actually, we can get some non-trivial lower bounds. So the best upper bounds in this setting are a little bit worse than the best upper bounds for disjoint repair groups. They look something like this. This is due to Polyanskaya, Polyansky, and Voroberev. But we are able to get some non-trivial lower bounds in this setting. So here's I'll just state the theorem and not prove it. It turns out that any t batch code has to have redundancy at least omega t root n. So we can at least get sort of some non-trivial lower bounds for batch codes, which maybe suggests that perhaps we could be able to do that for disjoint repair groups as well. Okay, I'm out of time. So I was going to tell you the proof of it because it's pretty short, but I'll skip that. Bad at time management. Okay, so to wrap up, just in summary, there are a whole bunch of different notions of locality in error correcting codes. And I hope I've convinced you that disjoint repair groups is a pretty fundamental one that shows up in a lot of different notions of locality throughout error correcting codes. And this shows up in a lot of different places, not just in error correcting codes, but it also has applications to distributed storage, private information retrieval, and so on. You can construct them with variants on lifted codes, like lifted multiplicity codes or wedge lifted codes. And I guess the end of the story is that there is still a lot we don't know about the combinatorial trade-offs involved with these things. So there's still big gaps. Yeah, so open questions. So first, can we close some of these big gaps? So for disjoint repair groups, the correct trade-off here between availability and redundancy could be anywhere in this region as far as we know. And for batch codes, it could be anywhere in this region as far as we know. These are big open questions. But the main open question that again, going back to what is this talk about with a capital A, that I wanted to impress on this audience is, what are some more applications of these notions? So hopefully I've given you a flavor of like what these are, how you get them. But I feel like they should have a lot more applications, especially algorithmic applications. They kind of have applications in the flavor of amortizing over multiple queries or doing load balancing stuff, which comes up in sublinear time algorithms, which all y'all are experts in. So I hope that you're able to, I hope that you're inspired by this talk to maybe think about some possible applications of these. Okay, yeah, so with that, let me wrap up. I want to make one ending announcement that there is a poster session right after this in the GatherTown link that Venkat just put in the description. And so I'll stop now. And yeah, thanks for all your questions during the talk. I'll take more questions now. Thanks.